Alrighty. So on Friday, what we were talking about was bijections between sets exist if and only if uh, the sets have the same cardinality. So we were going through and finding bijections between all of these sets to show that they have the same cardinality. You have one of these on your homework. I think it's the odd integers and the integers. Um, and then we did this. So there's levels of infinity. Countably infinite would be that there's a bijection with it and the integers. So you can make a list. And then we are trying to show that the real numbers are not countable. So they are uncountably infinite. So the thing that we were doing is, okay, well, if they're countable, then we can make a list. So we are going to assume that it's countable. We're making our list. This like chart basically of all these decimals, all of the decimals between 0 and 1. And because we're assuming it's countable, then we could list them all given enough time and no life, right? That's what we decided on Friday. The idea here, this is the Cantor diagonalization argument, is that you pick off the diagonal all the way down and you like write out that number. This, in theory, is another number in this list because this list includes all possible numbers between 0 and 1. With me so far? So this is another number that you could find at some point in this list. Okay. We're going to write down another number. This should have a decimal in front of it. We're going to write down another number, D, that is D1, D2, D3, so on up to Dn, where D1 is 1 if A and N is not 1. So if A1, 1 is not 1, make it 1. If it is 1, make it 2. Yeah? If A2, 2 is 1, make it 2. If it's not 1, make it 1. Yeah? So the idea is that this number will be different from every number in this list in at least one spot, the nth spot. Right? So, like, let's assume that this number is in this list somewhere. Well, D is going to be different from it at 2, 2. Because it's switching from what, if it's a 1, make it not a 1. If it's a 2, or if it's not a 1, make it a 1, right? So the idea is that this is a new number between 0 and 1 that's not in your list anywhere. And therefore, you can't make a list, so it's not countable. Very nifty argument. Trippy, but there. Yeah? What do you think? No? Not convinced? Processing. Corey, what do you think?
Yeah.
Okay.
Is there like an application of this?
Yeah, so knowing that certain sets that there can't be a bijection between them has some implications in applications of stuff in like abstract algebra or in real analysis stuff. If you're working with uncountable sets, that's different than working with countable sets. So, yes. And being able to tell, like, these sets have the same cardinality, there's a bijection between them, therefore, I can do this mapping and then treat this the same way that I treated this thing, right? So in math, you're always trying to basically take something that we understand and put those properties on something that we don't yet understand. And so if you can apply, like if you know something about the integers, right? Well, okay, well, what if we include the rationals? Can you say the same thing now? Okay, what if we step up and we move to the reals? But that step's a bigger step, and it's harder to make that because you're moving from the set that's countable to a set that's not. And so, like, but that's like how, somebody gets a PhD in math is that they discover something new in math. But the way that you do that is you take something that's known and you try to apply it to something else. Right, that's known about this particular set of numbers, maybe, or known in this setting. Does it apply over here? And so, like, that's how a lot of new math is discovered, is doing stuff like that. This works in this scenario. Can we apply it over here? So, big understanding of like big structure understanding. Like, can this apply in this situation or not? Sort of how the whole math thing works. Alrighty, that's the end of chapter 7. You feel good about chapter 7? 1-to-1 onto compositions, bijections. That's all chapter 7, I think. Good?
Yeah.
All right. Let's talk about sequences. A sequence is a list of things where order matters. We write a sub n for the nth term of the sequence. Curly braces a sub n to represent the entire sequence. If the sequence goes on forever, it's called an infinite sequence, and if not, it's finite. Okay. Good job, everybody. Let's write some of the entries in these sequences. So the sequence a sub n equals 1 over n. How could we, what's a sub 1? It is 1 over 1, which is 1. What is a sub 2? 1 half. What is a sub 3? Great. This sequence looks like this: 1, 1 half, 1/3, 1/4, and so on. Maybe you would stop this at 1 over n, I guess, since this is a finite sequence. And this is going to be equal to a sub n, or you could even write this like this, 1 over n, but in a sequence notation so that people know it's a sequence. In a curly braces notation. Alrighty. Okay. Number 2, we have a sub n is 2 times -3 to the n plus 5 to the n. Yeah. Okay, so a sub 1 is 2 times -3 to the first plus 5 to the first. -6 and 5 is -1. A sub 2 is 2 times -3 squared plus 5 squared. 25 and 18 is 43. A sub 3 is 2 times -3 cubed plus 5 cubed. That's 125 plus. Is that? No. 5 times 5 is 25 times 5 is 125, right? Oh, but that's negative. I was like, why is this number smaller? Because the other one's negative. I got it. 71 is what I have written down. I don't know what. That's 27 times 2, but negative. I have 71. How does that sound? Fine. Good. All right, so there are the first like 3 entries in that sequence. Do you have questions or no? Okay. What? No. Okay. 3, a sub n is n plus 1 to the n plus 1. So a sub 1 will be 1 plus 1, which is 2 to the 2. A sub 2 is 2 plus 1, which is 3 to the 3. A sub 3 is 4 to the 4th. Oh, 4, 9. It's hot in here, right? Oh, that's 27. Is it hot in here? There's something wrong with me. Is all the coffee catching up to me? 256. Y'all aren't answering. Okay.
It also smells kind of funky.
Oh, good.
Well, I was in the science building where Wofford said it was 59 degrees, so it just feels, I don't know.
And if you've ever been in the A&P room that Dr. Hardwick teaches in, like right when you walk into the science building, they just fixed the AC, but I'm pretty sure it was like 52 degrees on the thing. It was freezing every morning. He would bring his jackets to class and like hand them out. It was terrible. They just fixed it though, so I prefer this over that.
Yeah, well, that's fair.
And, so Dr. Wofford said that a lot of the air conditioning goes through the physical chemistry classroom, so it's just like
Freezing.
yeah.
Oof. Okay, we're going to find find an explicit formula for the sequence with these initial terms: 1/4, 2/9, 3/16, 4/25, 5/36, 6/49.
So we got n plus 1 squared.
This starts with n greater than 0, right? Or n greater than or equal to 1. But yes. So this sequence could be written like this as a sequence, or you can write a sub n equals n over n plus 1 squared. .7 we probably won't get to before the exam, which is fine. I never do. But it is basically doing this, but when the sequence is defined recursively, so like the third entry depends on the 2 before it or whatever. So anyway, hopefully we'll get there. But how about this one? We have 0, 1, -2, 3, -4, 5. You've got an alternating situation going on, so we're going to do -1, the like positive negativeness. -1 to some power is going to be the thing that does that. It depends on where we start. I would maybe start with n and make this, when I plug in 1, I want to get a positive, so this be an n plus 1. This would be for n greater than or equal to 0. So if we plug in 0, we get 0 times -1 to the first. That's -0, which is fine. Plug in 1. Like this would be n equals 0. This would be when n equals 1. Plug in n equals 1, you're looking at 1 times -1 squared. That'd be 1 times 1, which is 1. And then 2 be 2 times -1 cubed, which would be -2. Does that make sense?
Yes.
Have y'all done this in calculus yet?
Yes.
You have taken Cal 3, 2, whichever one you do
Calc
this.
2, we have
But I did this in Calc 2.
You haven't gotten to sequences and series yet in Calc 2.
about to today with like P series.
Oh, fun. Huh. Okay. All right. So this is Dr. Martinez will do a much better job of explaining sequences to you today. Sherrod says yes. Thanks. No, but you will learn more about it, and we're doing it in a specific context. So yeah.
More sense learning this.
Sherrod says the sequence diverges, which is true because the negatives. Okay. So summation notation, if m and n are integers and m is less than or equal to n, then the symbol, the summation from k equals m to n of a sub k is read like that. The summation from k equals m to n of a sub k means you add up the terms from the nth term to the nth term, right? So you start with this is an indexing situation. So you start with m, you go to m plus 1, m plus 2, m plus whatever until you get to n, and then you stop. Okay. So these are finite summations. So when you do these infinite, they're called series, and that's when you talk about them either diverging, converging, or diverging. Okay. If when you add them, it's approaching a thing, it has a limit, that's when a series converges. And if it doesn't, it diverges. Okay. So we are going to do this with some examples. You have at least one of these on your homework too, where you get to just do some easy adding and be done. So we're looking at the summation of k from k equals 1 to 5. So we're going to plug in k equals 1. We're going to do the first term, the second term, the third, the fourth, and the fifth, and then stop there. When k equals 1, that's 1. When k equals 2, that's 2. That's 3, that's 4. That's 5. I'm trying to explain something that isn't actually that hard and maybe making it so much worse. That's 10, 15. And then we're going to do the same thing going from 1 to 4, adding up the k squared terms. So when k equals 1, when k equals 2, when k equals 3, and when k equals 4. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Questions or comments so far? No. Okie dokie.
I like
Well, hold on to that feeling.
you say you can't do this?
No. No, I didn't say that at all. You can. I believe in you. Okay. In expanded, we're gonna write this in expanded form. So we're gonna write it. We're gonna write it like this. So we're gonna start with I equals 0. So we're gonna go with -1 to the 0 over 0 plus 1 plus. Now we're moving to I equals 1. That's not an I. I equals 1. That's a T with a dot on top. That's fine. -1 to the first power over -1. Oh, no, +1. My bad. That'd be weird. +1 plus 1 plus -1. This is I equals 2. So -1 squared over 2 plus 1. Oops, I got a little ahead of myself. Maybe I shouldn't have had that third cup of coffee today.
Maybe you needed it.
I think I did need it, but now I'm feeling like maybe it wasn't a good choice. I feel like my heart's beating a little too fast, you know? So we're going from I equals 1 all the way up to I equals n. And this is what those look like. I'm going to simplify those terms so we can see what they are, but -1 to the 0, that's 1. So that first term is just a 1. The second one, we're looking at -1/2. The third one is a +1/3. Ooh. Minus the 1/4 plus ... plus -1 to the n over n plus 1. This is an alternating series as well. But this one does converge, I think, to 0, right?
Because it's like, yeah. The series form would also converge.
Yeah, infinitely. Yes, that's what you mean. If that, yeah. Yep. Cool. Questions? Comments? No? Okay. We're going to do summation notation for this thing that's in expanded form right now. Because I see a like +0, +1, +2, I'm going to start with I equals 0. This be I equals 1. This be I equals 2. And go from there. So my summation is going to go from I equals, oh golly. My summation is going to go from I equals 0 to n. On the bottom, at least, I'm going to have I plus n or n plus I. And then what's up top? It's I plus 1, yeah. Yeah, I plus 1. I plus 1 up top, N plus I on the bottom. Okay, so that is 5.1. That's the end of homework 9, which is going to be due on Friday. This is the beginning of homework 10. Which will be due on Monday. I don't remember what the day is. The 4th? All right, ready? Okay, this is a big idea. It's called mathematical induction. This is a proof technique, a pretty important one. So we're going to talk about the idea first. So let's imagine that you have an infinite row of dominoes. What do you need to know, or what do you need to do so that all of the dominoes fall down?
Kick every single one of them.
Kick all of them. Done.
You never specified they were set up either.
They're not. I'm only allowed to touch one, maybe, after they're set up. I can, yeah. So how do I set them up so that they would all fall? It doesn't have to be a straight line, folks. You can turn dominoes. You can turn dominoes all over the place, right? But when we push one, what happens? It pushes the next one, right? And then that one pushes the one after it, right? So what you need to know is that the first domino falls.
Yes.
And if a domino falls, the one behind it will. That makes sense, right? That is how you would know that they were all going to fall, is that the first one falls, and anytime a domino falls, it knocks over the one behind it. Okay. How about if we want to know if we can climb all the way to the top of a ladder? What things do we need to know about the ladder? We don't need to know how tall it is or where it ends to know if we can climb it. We don't need to know how many rungs are on it either.
We just need to know that it has rungs.
We need to know it has rungs. If it's grounded, what do you mean by that? Expand that idea.
Like that it starts at like level 0.
That we could get on it, right? Like if it's floating, I can't get on that ladder, can I? Even if it's got a million rungs, I can't get on it, right? I need to be able to get on the ladder. On, that's an on, not a one. Can I get on the ladder? And then what else? Yeah, that if I'm on a rung, I can get to the next one. I don't know how to spell a ladder rung. Is it W-R-U-N-G?
W-R-O. It's like wrong, like right and wrong.
It is not. A ladder rung is W is wrong, is spelled wrong.
Maybe Google is
It's not spelled like this.
Sorry, yeah, it is R-U-N-G.
R-U-N-G.
Google is pulling up wrong letters.
If you run something out, you run out like a rag.
Yeah, like
Right.
you rung out a rag.
Yeah, I just want to know if that's the same kind of, if you spell the same way. English doesn't make any sense.
Wrong is the past participle of ring.
Yes. Does it also mean a step on a ladder?
Yeah, I swung myself onto the ladder and fell at the next rung.
Okay.
Yeah, I'm fact checking it in fact.
So to knock down a bunch of dominoes, you need to know that you can knock down the first domino, and that after that, every domino will knock down the one behind it. If you're trying to climb a ladder, and this is an analogy that makes more sense to you, then you want to know that you can get on the ladder at all, and then that once you're on the ladder, you have the ability to climb. So if you're on a step, you can get to the next step. Okay, so strong induction is just that. So, I mean, regular induction, strong induction is different. My brain went somewhere else. Okay, so if we were thinking about this in math, the sum of the first n integers, positive integers, is n times n plus 1 over 2. This in summation notation, y'all, just to get comfortable if you're not. In summation notation, this would be a sum from I equals 1 to n of just I. Right, so the sum of the first n positive integers is n times n plus 1 over 2. How would you prove that?
Take the 1 and the n and put them together, and 2 and the n minus 1 and put them together, and each thing would add to n plus 1, and you'd have n over 2 of them.
Are you going to do that for all of them? How do you know? How would you prove that each one would add to n plus 1?
You're going down by 1 and up by 1.
Mm-hmm.
So the plus 1 and minus 1 will always cancel out.
Mm-hmm. But you're taking some liberties, right, in saying this works all the time?
Yeah, I mean, I haven't fully worked out the proof.
Correct. But you really like couldn't, could you? Because this is an infinite. Well, you don't know what n is. This it would be hard to do to convince someone of by like a straight up proof, but we could do it with induction, and you would use that idea and say like it works like this, and you since it works here, it also works here and here and here and here, so that you don't have to show it for everything between 1 and n.
So the second exists.
Sort of at the beginning. So the idea of mathematical induction, I need you to know right now, I hate the way the textbook defines induction. I hate it. The PA, PK, PK plus 1 notation I find very confusing. I will not use it again after right now, and I'm only doing it so that you know what your book says about induction, and it is defined. It's fine. So P of n is a statement. This is a predicate, right? For some, remember way back when we were talking about like P of n is that n is greater than 2, right? This is true or false once you assign value to n. Yeah. So P of n is some statement defined for all integers n. It's a fixed integer. A is a fixed integer. So basically you need to know, or this is basically the ladder that you can get on the ladder, and that once you're on a ladder rung, you can climb to the next one. Or that you have knocked down the first domino, and that once you knock down a domino, it'll knock down the one behind it. So if these two things are true, if P of A is true, and for all integers greater than or equal to A, being on 1 means that it knocks the next one down. If those things are both true, then this is a true statement for all integers greater than or equal to A. Again, that notation I think is confusing, but this is an if-then statement. Notice this. So the way we're going to do induction proofs is that we're going to show it works for a base case. We're going to pick the starting value. We're going to show we can get on the ladder, or show that we can knock down the first domino. And then the inductive step, we're going to assume that we're on a particular ladder rung. So we're going to assume it's true for some k. And we're going to show that then we can prove that it is true for k plus 1. The k step implies the k plus first step. So think through this with me. Why would this be valid? Well, it's a whole bunch of modus ponens together. So the first step and the first step can knock down the second gives you number 2, right? And then the second one and that the second knocks down the third gives you number 3. The third step and the third knocks down the fourth, that gives you, 4. This is a whole bunch of modus ponens together. Maybe this is a better way to say it, and that's what I should have typed. So for the basis step or the base case, you want to show it's true when n equals a, whatever the lowest thing it's defined for is. And for the inductive step, you're going to assume it's true when n equals k, and then show it's true when n equals k plus 1. Okay, so let's try it now. We're going to do scratch work because Shania's here. I don't have a ton of space to do this proof, so I'm going to write real small, and you should also write quite small. That's how much space I'm leaving myself for scratch work.
That's what I would.
Okay. So there are a couple ways that we can write this. The sum of the first n positive integers. You can write that as I equals 1 to n of I is equal to n times n plus 1 over 2. Or you can write that instead of using the summation notation, you can just write 1 plus 2 plus 3 plus ... plus n. Whichever one you are more comfortable with, it does not matter. So the first thing that we want to know is, does this make sense for the smallest possible positive integer? So what is the smallest value here? What's our base case when n equals what? Yeah, so when n equals 1. So what is the sum from I equals 1 to 1 of I? It is 1. And what we want to know is, what is 1 times 1 plus 1 over 2? It's 2 over 2, which is also 1. So this checks out for n equals 1. Okay, and then what we want to do is assume that it works, assume true when n equals k. So we're going to, do y'all want summation notation or not summation notation?
Yes.
I like submission.
Okay, so we're going to assume we're going from I equals 1 to k of k, I mean. This is equal to k times k plus 1 over 2. We want to show the summation from I equals 1 that it's true for k plus 1. N equals k plus 1. So we want to show that the summation from I equals 1 to k plus 1 of I, I'm making these n's k plus 1s. We good? So we're making this k plus 1 times k plus 2 over 2. Yes? Yes? Okay. I don't have any more space, so we're going to just do it in the proof in a minute. But let me talk you through the strategy. You good? Janaya, you with me? I plugged in k plus 1 here, so it's k plus 1 plus 1. So your base case is when n equals 1. Assume it's true when n equals k, so replacing those with both k's. And then we want to show it's true when n is k plus 1. So k plus 1 plus 1, which is k plus 2. Okay. So strategy is, I mean, we did this. We're just going to show this as a proof with words. We're going to assume this thing. And then what we're going to do is, in between here, we're going to do a proof. So what we're going to assume, I was going to point at the board, but Eunice won't see that. So I'll point here. What we're going to do is basically write this down. And then in here, we're going to use this somehow to arrive at this, which is fine. This goes from 1 to k plus 1. So the summation from 1 to k is in here. And we're going to use that. Right? This summation goes from the first term all the way to k plus first term. Well, that means the terms from 1 to k are in there too. So we can use this idea. All right, let's write a proof. We did like summation notation. We will prove, sorry, this is so tiny. We will prove by induction I gotta scoot this out of my way. Oh, I could have just copied and pasted it down there. The sum from I equals 1 to n of I is equal to n times n plus 1 over 2. For the base case, this is showing we can get on the ladder. Let n equal 1. Notice the sum from I equals 1 to 1 of I is 1, and 1 times 1 plus 1 over 2 is equal to 1. Since 1 equals 1, the base case holds. Okay, so far what we have is that we can get on the ladder. We'll prove by induction that the sum of the first n positive integers is n times n plus 1 over 2. So positive integers, that means our lowest number is 1, so we're going to let n be 1, show it works then. We're going to look at each side of that equation separately. Y'all, the number of students who will write these two things next to each other and say they're equal before showing it is problematic. Separate them until they are actually equal, right? So do the left-hand side by itself, this side. Do the right-hand side by itself. Show that they're equivalent before you say so. Sound good? All right, so since 1 equals 1, the base case holds. All right, so we've done the base case. We have shown we can get on the ladder, or we have shown that we can knock down the first domino. What we want to do after that is assume that we can knock down the kth domino, and that the kth domino will knock down the k plus first. Or that once we are on the kth ladder rung, we can climb to the next ladder rung. Okay? So we're going to say something like that's called the inductive hypothesis. For the inductive hypothesis, assume for some k greater than or equal to our base case, so greater than or equal to 1, that the sum from I equals 1 to k of I is k times k plus 1 over 2. we are going to consider the left-hand side of our want to show thing. So we're going to consider the sum from I equals 1 to k plus 1 of I. And now my job is to do the middle stuff where that equal sign is. I got to do some things. I don't want to write this down yet, right? I cannot write that down yet. That's going to be the last thing I write down. Okay. So what I need to do is figure out what I can write down so far. What's actually true right now? Well, what I see is true is that I can split this sum into two sums. One picks up where the other leaves off. It's only got one entry, so it's not really a sum anymore, but I figured it'd be worse if I wrote it not as a sum. Do we agree that those two sums together would squish out the middle? We would go from I equals 1 to k plus 1. Yeah. All right. The inductive hypothesis says that this part right here is equivalent to k times k plus 1 over 2. What is the sum from k plus 1 to k plus 1 of I? It is just k plus 1, yeah. This is k squared plus k plus 2k plus 2 all over 2. I distributed in that first fraction, found a common denominator with the second, and then just squished them together. That's k squared plus 3k plus 2. Yeah. All over 2. I know that this is problematic and you shouldn't do this in your own proofs, but we don't have any space. So this is where we are. This is equivalent to k plus 1 times k plus 2 over 2. Which is what we were trying to get to. So, we have shown by induction that the sum from I equals 1 to n of I is n times n plus 1 over 2. And we are done. I'm going to speak maybe out of turn here because I know very little about computers. But whatever. I'll do my best. This sort of thing, when it is written like this, the sum, when it's written without the summation notation, and without any like ellipses or anything, it is called being in closed form. That means all you need to know is what n is, you plug it in and you're done. So as far as like computer programming goes, which of these would be more efficient for your program to run, which would take more memory, less memory, whatever. This would take more memory and more time to do than just this. So having a closed form of a summation is really good for both us by doing things by hand, but also for programs that are doing things not by hand. Cool. Okay. Not having to run the summation up to the 700th digit instead of just plugging in 700 is easier, right? So whether we are computers or humans, which we are humans. All right. So let's go on to page 18, and we're going to keep doing proofs. Hopefully we're going to have enough space. So I got pretty tight on space when I was doing this by hand myself, but we'll try. So we are going to prove that the sum of the first n odd integers is n squared. Hi, Eunice. The sum of the first n odd integers is n squared. So we're going to give some space for scratch work. What would the summation notation look like for the sum of the first n odd integers? Well, we're going to go from I equals 1 up to n. What would the first odd integer be? 1. Okay. What would the second odd integer be? 3. How do I plug this in and get 3? Okay. 2i minus 1. If I plug in 1, I get 1. If I plug in 2, I get 3. If I plug in 3, I get 5. That's good. Yes? Okay, so this would be like adding 1 plus 3 plus 5 plus all the way up to 2 to the n minus 1. What we're going to prove is that this you can compute in closed form by just doing n squared. Again, which is a lot easier than doing the summation. All right, so our base case for induction, remember we want to start with the smallest one, so it would be when n equals 1. So what's the summation from I equals 1 to 1 of 2i minus 1? It is 1. And you would say something like, also, 1 squared is 1. 1 equals 1, so we're good to go. Working left and right hand side separately. Don't say they're equal until you have proven that they are. Okay. So base case is good to go. We can knock down the first domino, or we can get on the ladder rung. First ladder rung. All right, inductive hypothesis. We are going to assume for some k greater than or equal to our base case that it's true. So we're going to assume from I equals 1 to k that 2i minus 1 is equal to k squared. So we assume that the summation works for some k value greater than or equal to our base case. We want to show that it's true for k plus 1. So I'm replacing everything with k plus 1s in the original setup. So base case n equals 1. Inductive hypothesis, we're going to assume n equals k, assume it works when n equals k, and then we want to show that that gives us that it works when n equals k plus 1. Okay, are we good to start writing a proof? Yes, maybe. We will prove by induction that the summation from I equals 1 to n of 2i minus 1 is equal to n squared. For the base case, let n equal 1. Notice the sum from I equals 1 to 1 of 2i minus 1 is 1, and 1 squared equals 1. Clearly, 1 equals 1, so the base case holds. For the inductive hypothesis, assume for some k greater than or equal to 1 that the sum from I equals 1 to k of 2I minus 1 is equal to k squared. Guys, the sum k greater than or equal to 1, this is how you do regular mathematical induction, is you assume it works for some ladder rung and prove that that gives you the next one. Strong induction, which we'll learn about later, Monday, you assume it works for all k up to a certain k. So it's very important here when you don't need strong induction that you don't assume it for more than just some k. Okay? A lot of you are going to fall into this trap where you're going to write for all k greater than or equal to 1. Like, if that were true, why are we proving it? Right? Like, if it's true for all k, if we're assuming it's true for all k, why are we doing anything at all? That makes sense, right? So when we do strong induction, we'll have like a stopping point. It's all of the values up to a certain k that it works for, and then we'll use that to prove the next one. That works when things are defined recursively, like to get to this ladder rung, you need to step down 2 and jump. And so you use strong induction because you get to assume all the ladder rungs before it work. But we'll get there Monday. For today, though, we're just assuming it works for some k greater than or equal to our base case. And then we're going to use this to show it works for k plus 1. So we're going to consider the sum from I equals 1 to k plus 1 of 2I minus 1. And I'm going to do the same kind of thing that I did before, where I'm going to split that sum into the thing that is my inductive hypothesis and then the leftover bits. So this is actually equal to the sum from I equals 1 to k of 2I minus 1. And then that, do I need to write this as a summation, or can I write just the entry? So that next thing isn't going to be a summation, it's just going to be an entry. Right, because it's going to go from k plus 1 to k plus 1, so there's just going to be one term. Okay. So remember, this in here is where we are right now. We're doing this proof. Don't write those next to each other yet, right? I wouldn't want to say here that this equals k plus 1 squared and then do a bunch of stuff. Like, if it already equals that, why are we doing anything? So don't say it yet. This is going to conclude with that in a minute. Yeah. But I've got to do the math now to figure out how to do that. So this bit, this thing is k squared. That's from the inductive hypothesis. And then we're looking at 2k plus 2 minus 1, so 2k plus 1. Which factors the k plus 1 squared? I'm doing this for your benefit. So we have shown by induction that the sum from I equals 1 to n of 2I minus 1 is equal to n squared. Look at that, I had extra space. Apparently I didn't need to write so small. You don't have extra space, do you, Eunice? No. No. Alrighty. Ready to do another one? Okay, so we've done it for summation things. This you can also use induction to do stuff like this to prove that for past a certain number that like this is true all the time. So that n factorial is less than n to the n for all integers greater than 1. This is helpful when you're trying to show if a series converges or not or something like that, you know, to know that this thing's always smaller than this. Right? Just helping you out a little bit, Cal 2 people. So we are going to do this as well with induction. So for our base case, we're going to assume it's, we're going to show it's true for n equals 1. Oh, greater than 1, sorry. So 2. So this is the temptation, like don't write this straight up. Don't write 2 factorial less than 2 squared, right? So you would say something like, notice 2 factorial is 2 and 2 squared is 4. Clearly, 2 is less than 4, so the base case holds. Do you know what a factorial is? It's the like 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Mm-hmm. Yep. Okay. For the inductive hypothesis, you want to assume it's true when n equals k for some k greater than or equal to 2.
It would be good to remember what the factorial is for a particular problem in this class. Just saying.
I've lost my train of thought. Oh, what is it that we get to assume? That k factorial is less than k to the k. What we want to show is that k plus 1 factorial is less than k plus 1 to the k plus 1. This is the proof in here. Students always tell me here, or we always talk about here, that the proof is in the pudding. The pudding is there in the middle. So don't write those things next to each other yet. Do the proof first. And then last year I got little proof bowls. It's a set of 4 little bowls that all have very famous proofs on them from my class for the proof being in the pudding. It's cute. What are y'all gonna do? Just kidding. Just kidding. It was Ruth. She owed me. Okay. So we've got n factorial less than n to the n for all integers greater than 1. We are going to show it works for n equals 2. Assume it works for n equals k for some integer k greater than or equal to 2. And then we're going to show that it works for k plus 1. All right, I'm going to write a proof now. Proof. We will prove by induction that n factorial is less than n to the n for all integers n greater than 1. For the base case, let n equal 2. Notice 2 factorial is equal to 2, and 2 squared is equal to 4. Clearly, 2 is less than 4, so the base case holds. For the inductive hypothesis, assume for some integer k greater than or equal to 2 that k factorial is less than k to the k. Now we're going to consider k plus 1 factorial. Now I've got to do some stuff and eventually down here say this is less than k plus 1 to the k plus 1, right? But I can't do that yet, so I got to be careful. What can I say?
Could you start by saying that k plus 1 factorial is just equal to k factorial plus k plus 1?
Times k plus 1, but yes. K factorial, k plus 1 factorial is just k factorial times k plus 1. Because k plus 1 factorial is k plus 1 times k minus 1 times k minus 2. And then, so k factorial hits all of those things except for the k plus 1 bit. Alrighty. What do we have now? Yeah, we can use our inductive hypothesis and say that this is less than k to the k times k plus 1. Now, these are the things students like least, maybe because you actually have to sort of come up with things out of thin air. So it allows space for you to be creative. And sometimes that space feels very overwhelming. But I need to get to a place where I have k plus 1 to the k plus 1. So I need to be able to make some mathematically true jumps here that get me there. So one of them I'm going to make, and this is fine as long as you keep the order of the things, right? So I could replace something that is equivalent or less than. I guess it would be greater than. Yeah. So I can replace something here with something that would maintain the integrity of this and not switch it back and forth. Because when you go back and forth, you can't say so. But if you've got a string of inequalities that go this way, then you can say that this is less than whatever's over here. Okay. So k is a number bigger than or equal to 2. Yeah. So k to the k is less than k plus 1 to the k. So this is the inductive hypothesis. That's how we got here. This is because k is less than k plus 1. And this is k plus 1 to the k plus 1. Because this has power of 1. Like bases, you add exponents. So you would say something like, thus k plus 1 factorial is less than k plus 1 to the k plus 1. So we have shown by induction that n factorial is less than n to the n for all integers n greater than or equal to 2. Questions or comments? No? Ready to keep going? Now, luckily on these divides ones, you don't have to come up with stuff from thin air and you don't have summations to work with either. So sometimes they're nicer to deal with, but you do have to make sure you use definition of divides and what it means. So if 2 divides n squared plus n, what does that actually mean? Yeah, that n squared plus n is 2k for some integer k. Y'all sort of are abusive of this notation a little bit. You like write this and then you do stuff on like either side of it, and that's really super weird. Don't do that anymore. We'll just like, state it and then what it means and then use that. Okay. So we're doing pretty good, I think. So if n is greater than or equal to 1, then 2 divides n squared plus n. What would our base case be? N equals 1. You would say, you wouldn't do this. You get what I'm saying? You wouldn't do this thing. Why? Because you're already saying it divides it, and we don't know that. And that's weird. Don't do that. Don't do that. And then you would like write this, and that doesn't make any sense either. Don't do that. Stop it. Just stop. You would say, okay, well, 1 squared plus 1 is 2, which is 2 times 1. So clearly, 2 divides 1 squared plus 1. Base case holds. For the inductive hypothesis, you want to assume for some integer k greater than or equal to 1 that 2 divides k squared plus k. What does that mean? That's his meaning, sort of. Emily, what does that mean? I'm going to use A. That's approximately where the I is in meaning. All right. And then what we want to show is that 2 divides k plus 1 squared plus k plus 1. Replacing my n's now with k plus 1's. Are we doing okay with that or not doing okay with that? Yes. So this is when n equals k. That's what you assume. You want to show it works when n equals k plus 1. All right. Again, this means what? Emily, what does this mean? Yeah, and that one I'm not going to name because I don't know what it's going to be. Okay. We will prove by induction that 2 divides n squared plus n for all integers n greater than or equal to 1. For the base case, let n equal 1. Notice 1 squared plus 1 is 2. Clearly, 2 divides 2, thus the base case holds. For the inductive hypothesis, why is he still talking? I mean, you're here and class ended 25 minutes ago. Why is he still talking? At 12:30. He's disturbing me. For the inductive hypothesis, assume for some integer k greater than or equal to 1 that 2 divides k squared plus k. Oof. That is k squared plus k equals 2 times a for some a in z. Your test is a week from today? From next Friday. So I have 3 more classes after today. Just 2.
2 more.
Today is Monday, not Friday. Got it. That was quite a shock. Okay, today is Monday, so I have this Friday and next Monday. And your test is a week from Friday.
Yes.
Okay. Great. Alrighty, we're going to consider this side of things because that's how we're going to do the proof part. So we're gonna consider k plus 1 squared plus k plus 1. Homework 9, you two. Homework 9 is due Friday. Homework 10, Monday. Homework 11, next Friday. Corey, did you get that?
Yes.
He did not.
I heard her read. I was here when you talked about that.
For all 3?
Yeah.
I thought I told y'all to remind me to say it once Eunice got here to both of them.
Well, you were saying Corey and then you corrected yourself as you walked in.
Oh, bummer. All right, sorry, Corey. Eunice, you got it? Okay. This is k squared plus 2k plus 1 plus k plus 1. Watch this, folks. That's k squared plus k. I'm not going to combine that with that 2k. That's all right, because those are both divisible by 2, aren't they? And guess what else is? I know, pretty cool, right? That's 2a plus 2k plus 2. And then you can factor a 2 out, obviously. That's a plus k plus 1. And you would say since a plus k plus 1 is an integer, 2 divides k plus 1 squared plus k plus 1. We have shown two divides n squared plus n for all n greater than or equal to 1. I don't care. I already said at the top that we were doing it by induction. Why don't you go? Oh, you have homework to do. Never mind. Do your homework before I see you on Friday. Try your homework 10 because it's just regular induction. See if you can do it. That's the one that's due Monday. So you can ask me questions on Friday. Cool, cool.
This time I don't plan on having a biochemistry.
Good. And I'll have graded homework for you back then too. Okay. Yes. Nope. I'm going to write it down right now in my planner so that I don't forget again. Grade Jacob's homework. Maybe soon. Yeah. I'll give you a point per week it's been that I didn't give you any feedback. How about that?
I'll loan you a due date.
Okay. Thank you. I don't know what the online homework looks like. Somebody let me know if that's problematic. I don't know what it looks like. It got off, so I don't know if we're still off. All right. Eunice, we've got 2 people signed up for tutoring this afternoon if you want to go.